Good morning, everyone. This is the session 14 from the chapter of work, power, and energy. The topic is coefficient of restitution, and this will be a very small session, maybe of 5 to 6 minutes, in which I will be just discussing about this coefficient of restitution. Now, the coefficient of restitution is denoted by E, that is small e, and this is equal to the relative velocity of separation divided by the relative velocity of approach. Now here, in order to explain it, I have made a very simple diagram in which I have taken two bodies which are moving with different velocity before collision, and after this is before collision, and after the collision their velocity becomes v1 and v2 respectively. That is, u1 is the velocity of this body A before collision, and after the collision its velocity becomes v1, and u2 is the velocity of this body B, which becomes v2 after collision. So here the coefficient of restitution, which is denoted by small e, is given by relative velocity of separation. So here the relative velocity of separation is v2 minus v1. See, these two bodies will get separated when v2 is more than v1. Okay, so the relative velocity of separation will be v2 minus v1. Now here, before the collision, that is the relative velocity of approach, means here these two bodies will collide when the velocity, that is when the velocity of A is more than the velocity of B, that is u1 is greater than u2. So here the relative velocity of approach before the collision will be given by u1 minus u2. So this is the formula for the coefficient of restitution, which is equal to relative velocity of separation divided by the relative velocity of approach. So in this case, this will be equal to v2 minus v1 divided by u1 minus u2. Now, for an elastic collision, E is equal to 1. It implies that u1 minus u2 will be equal to v2 minus v1. If I put the value of E as 1, then I will be getting u1 minus u2 is equal to v2 minus v1, or simply we can say that it implies that relative velocity of approach is equal to relative velocity of separation. From this formula, we can simply say that the relative velocity of approach, this u1 minus u2 is the relative velocity of approach, and v2 minus v1 is the relative velocity of separation. Okay, so for an elastic collision, the relative velocity of approach is equal to the relative velocity of separation. And for the inelastic collision, for a perfectly inelastic collision, E is equal to 0. For a perfectly inelastic collision, E is equal to 0. So it implies that if E is equal to 0, then V2 minus V1 is equal to 0, or V2 is equal to V1. Okay, V2 is equal to V1, or in other words, we can also say that for in the case of a perfectly inelastic collision, both these two bodies stick together after the collision and they move together. So if they move together, then we can find their this common velocity. For a perfectly inelastic collision, E is equal to 0, so V2 is equal to V1, or we can say that in the case of a perfectly inelastic collision, the two bodies, they stick together after the collision and move together with a common velocity. So in this case, we can find the value of the common velocity. So now we know that in all the types of this collision, the total linear momentum is conserved. So we will be applying this concept in order to find the common velocity in case of a perfectly inelastic collision. So here, in this case, I have from this diagram, the initial velocity, or you can say the velocity of this body A is u1, and the velocity of this body B is u2 before the collision. So the total momentum before the collision will be the total linear momentum before the collision should be equal to the total linear momentum after the collision. Now for a perfectly inelastic collision, the total momentum before the collision is equal to m1 u1 plus m2 u2, where m1 is the mass of this body A and m2 is the mass of this body B, and this will be equal to what? See, for a perfectly inelastic collision, both these bodies will stick together and they will move together with a common velocity. So here the mass will be equal to m1 plus m2, and the common velocity I have taken here as v. So in this case, for a perfectly inelastic collision, the common velocity v, or we can write this like this: common velocity v will be equal to m1 u1 plus m2 u2 divided by m1 plus m2. So after the collision, both these two bodies will move with this common common velocity, and with the help of now, as we know that in the case of the inelastic collision, the total kinetic energy before the collision is not equal to the total kinetic energy after the collision. So we can also find the difference in the the difference in the total kinetic energy before the collision and after the collision if we know the value of this common velocity. So the total kinetic energy before the collision is equal to, I'm just talking in terms with reference to this example. So here this will be equal to half m1 u1 square plus half m2 u2 square. So this is the total kinetic energy before the collision, and after the collision the total kinetic energy after the collision will be equal to half m is now equal to m1 plus m2 half m v square, and v is here is given by m1 u1 plus m2 u2 divided by m1 plus m2 whole square. So this is the total kinetic energy of after the collision, because here this half m will be equal to m1 plus m2, and v square, v is this is the common velocity after the collision, so I have put this value here, that is m1 u1 plus m2 u2 divided by m1 plus m2 to the power 2, that is whole square. So now since, as I have told you, that in the case of this inelastic collision, the total energy before this before the collision and after the collision is not the same, so we can find the difference in the total kinetic energy before and after the collision by using these two formulas. So this was a very short session. In the next session, I will be coming up with a question based on this topic. So till then, have a nice day. Bye.